The night sky makes the stars feel close. They seem to hang just beyond the darkness, bright enough to guide ships, mark seasons, and fill the horizon with familiar patterns. Yet the nearest star beyond the Sun is so distant that its light needs more than 4 years to reach Earth, while our fastest spacecraft would need tens of thousands of years to cross the same space. Between us and Proxima Centauri lies no dramatic barrier, only a quiet emptiness so wide that speed, fuel, communication, and even the length of a human life become serious limits. So why is reaching the nearest star far more difficult than simply building a faster spacecraft? Before we begin tonight's journey, subscribe if you want more calm space documentaries like this. Leave a like if you enjoy deep space mysteries. And here is a question. If you could send one small object from Earth to the nearest star, knowing you would never see it arrive, what would you choose? Let me know in the comments. I will pin the most creative answer. Tonight, you are watching the Just About Space channel, talking about why the nearest star is almost impossible to reach. On a clear night, they appear fixed to the same dark surface, bright points arranged into familiar shapes. Orion rises with the same outline. The Big Dipper turns slowly around the northern sky. Centaurus remains part of the southern darkness, its stars seeming close enough to belong to one quiet pattern. The stars inside a constellation are not usually gathered together in one small region of space. Some are much closer to Earth than others. A few may be physically related, but many only appear side by side because we happen to view them from the solar system. The lines people have drawn between the stars would stretch, bend, and disappear. A star that now forms the shoulder of a familiar figure might move far behind another. A shape that has guided travelers for centuries would no longer exist. Every star is placed on the same curved sky, while its true distance remains hidden in depth. The result is an illusion of closeness, so convincing that it shaped human stories long before the scale of space was understood. They moved across the sky together because Earth was rotating beneath them, and their relative positions changed too slowly to notice across one lifetime. Nothing in ordinary experience revealed that one star might be tens, hundreds, or thousands of light years further away than another point beside it. A bright star can feel closer than a faint one, though brightness depends on both distance and the amount of light the star produces. A massive blue star may remain visible from far across the galaxy, while a small red star can be almost invisible, even when it lies close to the Sun. It lies in the same general direction as Alpha Centauri, a much brighter pair of Sun-like stars that appear as one point from Earth. Together, the three stars form a gravitationally connected system, although Proxima sits much farther from the central pair. It produces only a small fraction of the Sun's visible light, and from Earth it appears so faint that a telescope is required to see it. The closest known star beyond our own shines invisibly in the darkness. The stars that dominate the night sky are not necessarily the stars closest to us. They are the ones bright enough to be noticed across immense distances. Their light began traveling long before anyone alive today was born. When we look at them, we do not see their present state. We see the light they released in the past. A star may have changed during that time. It may have expanded, collapsed, or exploded, while its older light continues crossing space toward Earth. Proxima Centauri is much closer than those distant giants, but even its light requires more than 4 years to reach us. Every observation shows Proxima, as it was more than 4 years earlier. If something changed there tonight, Earth would remain unaware until years had passed. Human beings plan projects lasting longer. Children grow through several school years. Space missions can remain active for decades. It is the distance light travels in 1 year, moving at nearly 300,000 kilometers every second. Light can cross the distance between Earth and the Moon in a little more than 1 second. It reaches the Sun in about 8 minutes. It crosses the orbit of Neptune in a matter of hours. A full year passes before that same light has traveled 1 light year. Proxima Centauri lies more than 4 of those distances away. The planets appear widely separated when measured in kilometers. Mars can lie hundreds of millions of kilometers from Earth. Jupiter is farther. Neptune orbits billions of kilometers from the Sun. Spacecraft require months or years to move between the planets because they travel far below the speed of light. Yet all of those planetary distances fit comfortably inside the gap to the nearest star. If the Sun were reduced to the size of a small coin, Earth would orbit several meters away. Neptune would lie far across the same field or building. At the same scale, it would be separated by hundreds of kilometers. The exact comparison changes with the size chosen for the model, but the result is always the same. The nearest star does not sit near the edge of the solar system. There are no planets marking each stage of the route, no bright stations, and no chain of stars leading outward. Small bodies, dust, gas, and wandering objects may exist in interstellar space, but they are spread so thinly that the journey would feel like crossing an ocean without islands. The solar wind creates a vast bubble called the heliosphere, extending far beyond the planets. Voyager 1 crossed the heliopause and entered interstellar space, but even that achievement did not place it close to another star. Distant, icy bodies may orbit in the Oort cloud, a roughly spherical reservoir surrounding the solar system, at extreme distances. Its outer edge is uncertain, and some objects may travel so far from the Sun that passing stars and the galaxy itself influence their orbits. Even if the Oort cloud extends tens of thousands of astronomical units away, it does not fill the full gap to Proxima Centauri. The solar system fades into interstellar space long before the next stellar system begins to feel near. Near the Sun controls the motion of planets and comets. Near Proxima Centauri, another star shapes its own local system. Between them lies a broad region where neither star creates the kind of familiar environment found close to a sun. At first, our star would remain the brightest object in the sky. The planets would disappear almost immediately, becoming too small and faint to separate. The constellations would slowly distort because the spacecraft's viewpoint had changed. Nearby stars would shift against the more distant background, revealing the three-dimensional structure hidden from Earth. The distance would shrink in mathematical terms while still feeling almost unchanged to the eye. A planet grows visibly larger during the final approach because the spacecraft has crossed a manageable fraction of the distance. On a journey between stars, the destination can remain visually small for years, centuries, or far longer, depending on speed. Around them, the rest of the galaxy would look almost fixed, because even a long human journey would cover only a tiny fraction of interstellar space. There would be no nearby landscape sliding past the windows, no surface beneath the spacecraft, and no horizon showing progress. Human beings experience travel through passing landmarks. Roads, coastlines, clouds, and cities show that a destination is getting closer. A spacecraft could move faster than anything humans have ever built, and still appear suspended in darkness. The nearest star would remain distant not because the spacecraft had stopped, but because the gap was too large for ordinary speed to matter. The Milky Way is often shown as a crowded spiral filled with bright stars, but the image compresses enormous distances. Stars look close together because the full galactic disk has been reduced to fit on a screen. If the scale were expanded until the solar system became visible, most nearby stars would be separated by wide, empty regions. Hundreds of billions of suns can exist inside the Milky Way without forming a continuous field of light. Their separation allows planetary systems to remain stable and galaxies to pass through one another without most stars colliding. But that same separation makes travel from one system to another extraordinarily difficult. A gap of several light-years is normal in the region around the Sun. Some stars pass closer to one another, Others are separated by much greater distances. The solar system exists in a relatively quiet part of the Milky Way, away from the dense central regions where stars are packed more closely. That quiet environment may have helped Earth remain stable across long periods. Nearby stellar encounters are rare. The planetary orbits are not constantly disturbed by passing suns. The same distance that prevents frequent stellar disruption creates a barrier against travel. A rocket can continue moving through the emptiness as long as its systems survive. Nothing in interstellar space demands that it turn back. Yet every kilometer crossed reveals how many remain. Humanity reached the moon by increasing speed, improving navigation, and supporting a crew for days. Robotic spacecraft reached the outer planets by surviving for years. An interstellar mission would not be the same challenge made slightly larger. It would force nearly every part of the journey into another category. Travel time becomes longer than human lives. Communication becomes delayed by years. Machines must operate beyond any possibility of repair from Earth. Even identifying progress becomes difficult because the destination remains a distant point for most of the route. They are separate suns floating across a volume so large that their apparent closeness is created only by distance and perspective. It joins stars that have no connection and makes remote objects appear like neighboring lights. Proxima Centauri escapes that illusion only through measurement. Its position shifts slightly against the distant background as Earth travels around the Sun. This effect, known as parallax, allows astronomers to estimate distance through geometry. Nearby stars move more noticeably than distant ones, but even Proxima changes position by less than 1 arcsecond from one side of Earth's orbit to the other. Modern instruments can measure that shift with extraordinary precision. From it, the depth of the sky begins to appear. Stars separate from the flat surface of the constellations and take their true places in space. Proxima emerges as the nearest point beyond the solar system, while the brighter Alpha Centauri stars lie only slightly farther away. Beyond them, other nearby systems appear at distances of 6, 8, 10, or more light-years. On a map of the local stellar neighborhood, the Sun becomes one point surrounded by other points. The arrangement may look compact on paper, but every line connecting those points represents years of travel, even for light. A scale model large enough to show the solar system would send the nearby stars far beyond the page. The map compresses emptiness so that it can be understood at all. This is the same problem faced whenever the universe is shown visually. If the planets are drawn large enough to see, the distances between them must be reduced. If the interstellar distances are shown accurately, the stars become too small to display. A complete model cannot preserve both size and distance while remaining practical. The mind is therefore given separate pictures and asked to combine them. A large sun, tiny planets, a distant Proxima Centauri. The true relationship between those images is easy to lose. When the scales are combined, the nearest star stops feeling like a neighbor. It becomes the first visible marker beyond a region of darkness vastly larger than the solar system. And Proxima itself is only the closest member of a much larger galaxy. Reaching it would not mean crossing the Milky Way. It would mean moving from one point to the nearest point beside it. The journey would be the smallest possible step between stars. That is what makes the distance unsettling. If the nearest destination already lies beyond the practical reach of current spacecraft, then the rest of the galaxy is not simply farther away. It is built from repeated gaps of the same impossible scale. A trip to a star, 100 light-years away, would cross the Proxima distance more than 20 times. A journey across the Milky Way would require tens of thousands of such steps. The galaxy can appear crowded only because the distances have been compressed into an image. From inside it, every destination is separated by darkness. The night sky does not show this emptiness. It covers the gap with light. Each visible star gives the impression that another place is waiting nearby. while the distance between us and even the closest one is almost impossible to feel. Only when that first gap is measured does the true problem begin to appear. And once the apparent closeness of the stars had dissolved, the small number of 4 light-years could finally be opened into the almost unimaginable distance it truly represents. Proxima Centauri lies about 4.24 light-years from Earth. Written on a page, the number looks modest. 4 years is shorter than many university degrees, shorter than the working life of several spacecraft, and short enough to feel almost familiar. But a light-year is not a measure of time. It is the distance light travels in 1 year, while moving at nearly 300,000 kilometers every second. At that speed, light can circle Earth several times in a single second. It reaches the Moon in a little more than 1 second and crosses the distance from the Sun to Earth in about 8 minutes. To reach Proxima Centauri, that motion must continue for more than 4 full years. The distance is close to 40 trillion kilometers. The number is so large that the zeros stop carrying meaning. Earth is about 40,000 kilometers around. The Moon lies roughly 384,000 kilometers away. Proxima Centauri is more than 100 million times farther from us than the Moon. Even that comparison is difficult to feel because both numbers belong to different scales of experience. A trip across Earth passes through cities, coastlines, weather, and changing landscapes. A trip to the Moon leaves one world visibly behind, while another grows larger ahead. Across 4 light-years, almost the entire route would contain no large object, showing that progress had been made. The spacecraft would move through distance, without moving through scenery. The delay in light offers one of the clearest ways to understand the gap. Sunlight takes around 8 minutes to reach Earth, so the Sun is always seen slightly in the past. Signals from Mars can require many minutes. Messages from the most distant spacecraft take hours. Near Proxima Centauri, the delay would be measured in years. A radio message leaving Earth would need more than 4 years to arrive. An immediate reply would need more than 4 years to return. One question and answer would take almost a decade. The distance therefore separates more than 2 stars. It separates decisions, warnings, discoveries, and conversations across years of silence. If something changed near Proxima tonight, Earth would not know until the middle of another decade. If a spacecraft there reported a serious problem, any instruction sent from Earth would arrive long after the crew or machine had already been forced to act alone. Nothing physical blocks the message. The message simply cannot move faster than light. The solar system looks very different when placed inside the same scale. Earth orbits 1 astronomical unit from the Sun. Neptune lies roughly 30 astronomical units away. The heliosphere extends much farther, and the distant Oort cloud may reach tens of thousands of astronomical units into space. Proxima Centauri is around 268,000 astronomical units from the Sun. The planets occupy only a small inner region of the total gap. Even the possible outer reaches of the Oort cloud would not bridge the full distance to the nearest star. Leaving the planets behind would not mean that another system was beginning to feel close. It would mean the long interstellar crossing had only started. A scale model makes this difference more visible. Suppose the distance from Earth to the Sun were reduced to 1 meter. Neptune would orbit about 30 meters away, somewhere across a large building or open field. Proxima Centauri would lie more than 260 kilometers from the model Sun. The entire planetary system could fit inside one local area, while the nearest star would stand in another city. Any model that brings Proxima close enough to display comfortably must shrink the planets until they are nearly impossible to see. This is why pictures of interstellar travel are always misleading in some way. A spacecraft is often shown between 2 large stars, both visible in the same frame. The image explains direction, but it cannot preserve the true relationship between size and distance. If the separation were drawn accurately, the stars would be tiny points surrounded by an image made almost entirely from empty space. Maps of nearby stars create the same illusion. The Sun and Proxima may appear as points separated by a short line, yet that line represents 40 trillion kilometers. The map removes almost all of the emptiness, so the destinations can fit on the page. Language compresses it as well. The phrase nearest star makes Proxima sound like the next stop beyond the planets. In reality, nearest is only a ranking. It does not mean easy, close in human terms, or reachable with the technology already moving through the solar system. Every other known star is farther away. That is the quiet meaning hidden inside the title. A spacecraft entering the wider system would still face distances enormous compared with the space between planets. It would need to approach the correct star at the correct position while every object continued moving through the galaxy. Proxima is not fixed in the sky. The Sun, Proxima, and all nearby stars orbit the center of the Milky Way while moving relative to one another. Over thousands of years, their positions change. For a fast probe, that motion can be predicted without transforming the mission completely. For a spacecraft requiring many millennia, the destination would travel a significant distance during the crossing. The route would need to aim not at where the star appears when the craft leaves, but at where it is expected to be when the craft arrives. A small navigational error could become a vast miss. Distance turns precision into a long-term requirement. It also changes the meaning of speed. These vehicles could never operate in space or survive those times, but the comparison shows how little ordinary speed matters once the destination is measured in light years. Even 100 kilometers per second would not solve the problem. At that speed, a spacecraft would cross more than 8 million kilometers every day. It could travel from Earth to the Moon in about an hour. Yet Proxima Centauri would remain more than 12,000 years away. A speed that feels extreme near Earth becomes slow between stars. This is the point where interstellar distance stops behaving like an expanded version of planetary travel. The challenge changes category. A spacecraft operating for 50 years is considered exceptionally durable. Against a 12,000-year journey, those 50 years cover less than half of 1% of the route. The machine could outlive every mission ever launched and fail while the destination remained almost as distant as before. Time becomes another part of the distance. Electronics degrade. Power sources weaken. Radiation damages materials. Tiny particles strike surfaces. Moving components wear down, and systems designed by one civilization may need to keep working long after that civilization has changed beyond recognition. On Earth, machines can be repaired. Between stars, every replacement part must already be on board, or the spacecraft must be capable of repairing and rebuilding itself. A failure would arrive at Earth as a signal years after it happened. Any response would require years more to reach the craft. The distance becomes a barrier made from delay. There is no physical wall between the Sun and Proxima Centauri. A spacecraft pointed correctly could continue moving through the darkness as long as its systems survived. But there is also no shorter route. A curved path can avoid hazards, yet it only adds distance. No demonstrated technology can open a shortcut through space-time. The only method known to work is movement across the space between the stars. That movement must cover the full gap. Relativity places another limit above every design. An object with mass cannot be accelerated to the speed of light with any finite amount of energy. A spacecraft does not need to reach light speed to make the journey useful, but even a small fraction of it is far beyond ordinary propulsion. 10% of light speed is about 30,000 kilometers per second. At that speed, Proxima Centauri could be reached in several decades, rather than thousands of years. But 30,000 kilometers per second is not a modest improvement over current spacecraft. It is a leap of several orders of magnitude. The energy would be enormous, and the spacecraft would need protection from interstellar gas and dust. The space between stars is extremely thin, but it is not perfectly empty. At ordinary speeds, a tiny grain of dust is a minor hazard. At a significant fraction of light speed, the same grain can strike with destructive energy. The distance creates the need for speed, and the speed changes the emptiness into a danger. Travel slowly, and the spacecraft must survive for longer than recorded civilization. Travel quickly, and propulsion, heat, shielding, navigation, and braking become severe problems. Proxima Centauri is where these difficulties appear in their smallest possible form. It is not a remote target selected to make the mission dramatic. It is the nearest known star. If the minimum journey already demands technologies far beyond present spacecraft, the rest of the galaxy becomes even more distant. A star, 100 light-years away, is not merely farther on the same road. It requires crossing the Proxima Gap more than 20 times. A journey across the Milky Way would repeat it tens of thousands of times. The galaxy looks crowded because its scale has been compressed into photographs and diagrams. From inside it, each star remains separated from the next by years of travel for light, and far longer for matter. The unsettling part is that the gap is not mysterious. Astronomers know the distance with great precision. They can measure the star's motion, estimate routes, and calculate travel times for different speeds. The obstacle is not uncertainty about where Proxima is. It is the difference between a journey allowed by physics and a mission that can actually succeed. A craft could cross the distance in principle, but reaching a star must mean more than passing through the same region. The spacecraft must still work when it arrives. Its instruments must collect useful information. Its communication system must return that information across another 4 light-years. If people are on board, they must survive the crossing and the destination. A dead probe drifting past Proxima has traveled there, but it has not completed an exploration. A craft moving too quickly to observe the system clearly may cross the distance without experiencing arrival in any meaningful sense. The 4 light-years must be crossed with purpose. That requirement connects every problem to the others. Speed controls travel time. Travel time controls durability. Durability affects mass and redundancy. Mass affects propulsion. Propulsion affects energy. Energy affects the size, cost, and complexity of the mission. Improving one part can make another part harder. The number 4.24 therefore contains much more than a distance. It contains years of communication delay, thousands of years at plausible spacecraft speeds, moving targets, long-term navigation, and machines that must operate beyond rescue. Before deciding how such a journey might be made, the distance must be compared with what humanity has already achieved. Our most distant probes have traveled for decades. They have crossed billions of kilometers, passed the giant planets, and entered interstellar space beyond the main influence of the solar wind. These missions are among the greatest technological accomplishments ever completed, yet their paths cover only a tiny fraction of 40 trillion kilometers. Placed on a true interstellar scale, they have not meaningfully approached Proxima Centauri. They have only begun showing how slowly human technology escapes the neighborhood of the Sun. And once 4 light-years had become 40 trillion kilometers, years of signal delay, and thousands of years of travel, the only useful comparison left was the quiet outward motion of the spacecraft already carrying humanity's instruments into interstellar space. It left Earth in 1977, past Jupiter and Saturn, and continued outward long after its original planetary mission had ended. Decades later, it crossed the heliopause, the region where the solar wind gives way to the surrounding interstellar medium. A functioning spacecraft had finally moved beyond the main bubble created by the Sun and entered the space between stars. The spacecraft continues traveling at roughly 17 kilometers per second relative to the Sun. At that speed, it covers more than 1 million kilometers each day. Nothing built by humanity has traveled so far from Earth while remaining capable of sending information home. The numbers sound enormous until they are placed beside the distance to Proxima Centauri. At Voyager's present speed, crossing 4.24 light-years would take around 75,000 years. The spacecraft would not actually reach Proxima because it is moving in another direction. But the travel time reveals the scale of the problem. Against an interstellar journey lasting tens of thousands of years, that achievement represents only the earliest beginning. If a Voyager-like spacecraft had been launched toward Proxima Centauri when modern humans first appeared, it might be approaching the system around the present era. If it had left when the oldest known cities were being built, it would still have most of the journey ahead. A machine designed by one civilization would need to survive through the rise and disappearance of many others before reaching the nearest star. Its systems were designed for a journey through the outer solar system, not for operating across geological stretches of time. Its nuclear power source gradually weakens, and its instruments have been turned off one by one to preserve the remaining electricity. Eventually, the spacecraft will no longer have enough power to communicate. The dark hull, antennas, cameras, and golden record will drift outward without guidance, carrying evidence of humanity long after the last usable signal has faded. Voyager is moving through interstellar space and will pass other stars over immense periods of time. But drifting near a star tens of thousands of years from now is not the same as reaching a chosen destination. The spacecraft will not enter orbit, slow down, or direct its instruments toward a planned target. Its trajectory was shaped by the planetary encounters that completed its original mission. The stars it passes will simply happen to move near that path, as the Sun, the spacecraft, and the rest of the local galaxy continue their separate motions. Voyager is therefore less like a ship sailing toward another shore, and more like a message released into a current. It does not prove that they can cross interstellar space within a useful time. The distinction becomes clearer when the journey is compared with the size of the heliosphere. That boundary lies roughly 120 astronomical units from the Sun, though its exact distance changes as the pressure of the solar wind and surrounding medium varies. On the scale of the nearest star, it becomes a small region surrounding the Sun. A mission can travel farther than any previous machine, leave the planetary system, and enter a new physical environment, yet still make almost no visible progress toward another star. The names sound related, but the gap between them is thousands of times larger. It followed a different path through the giant planets, becoming the only spacecraft to visit Uranus and Neptune before continuing toward interstellar space. Its journey transformed the distant solar system from points of light into real worlds with weather, moons, rings, and magnetic fields. But after completing those discoveries, Voyager 2 entered the same immense emptiness. Pioneer 10 and Pioneer 11 are also leaving the solar system, though communication with them ended long ago. New Horizons, which flew past Pluto and later a smaller Kuiper Belt object, continues outward on another path. None was designed to survive long enough to reach any star as an active mission. Still, together they show the best humanity has achieved with spacecraft, allowed to coast away from the Sun. Most of the acceleration occurred during launch and close encounters with planets. A spacecraft can use a planet's gravity to change direction and gain speed relative to the Sun. This technique allowed the Voyager missions to move from one giant planet to another using an alignment. That occurs only rarely. Gravity assists are elegant because they use the motion of planets rather than requiring the spacecraft to carry all the fuel needed for each change in velocity. The planets themselves move at tens of kilometers per second, not thousands. A gravity assist can reshape a route and add valuable speed, yet it cannot accelerate a heavy spacecraft to a meaningful fraction of light speed. Once Voyager left the major planets behind, there were no larger worlds waiting farther out to provide repeated boosts. Voyager can continue at roughly the same speed for millions of years, unless gravity or a collision changes its path. This sometimes creates the impression that the propulsion problem is simple. On Earth, engines must continue working because friction and air resistance constantly remove speed. Once a spacecraft reaches a velocity, it can keep that velocity without burning fuel. The difficult part is creating the velocity in the beginning. Voyager's 17 kilometers per second is fast because rockets had to lift the spacecraft away from Earth, escape the sun's gravity, and place it on a route through the outer planets. Increasing that speed by a small amount already requires substantial energy. Increasing it by a factor of 10 requires far more than 10 times the kinetic energy. At 100 times Voyager speed, the journey could fall below 1,000 years, yet the spacecraft would need to move at roughly 1,700 kilometers per second. Even this extraordinary speed would remain below 1% of the speed of light. A mission lasting centuries might be imaginable for a self-repairing machine, or a civilization willing to begin a journey whose creators would never see the result. For scientific exploration, even a robotic mission must preserve power, instruments, memory, and communication through a duration longer than the history of modern technology. The spacecraft could not depend on spare components designed to sit unused for 1,000 years. Software would need to handle situations its original designers could not predict. The mission would become less like operating a spacecraft and more like creating an artificial organism capable of maintaining itself. Its longevity is remarkable, but it has required constant attention from engineers on Earth. Commands are carefully planned, faults are analyzed, old documentation is studied. Systems are reconfigured to work around failing components and declining power. A probe halfway to Proxima would be years away from Earth by radio. A fault report would arrive years after the fault occurred. Voyager's slow outward journey, therefore, reveals two limits at the same time. Making the craft faster would reduce travel time, but it would also increase the violence of the journey. At 17 kilometers per second, interstellar dust is a concern over immense durations, but individual collisions are not comparable with those at relativistic speeds. At thousands of kilometers per second, small particles carry far more destructive energy. At a significant fraction of light speed, even tiny grains can threaten the spacecraft. A spacecraft falling very close to the Sun can move extremely fast, as gravity accelerates it inward. If a propulsion system or solar sail acts near the closest approach, the craft may leave the solar system with a much higher speed than a direct launch from Earth could provide. Parker Solar Probe has become the fastest human-made object during its close passages around the Sun. Its peak speed relative to the Sun reaches hundreds of kilometers per second. Yet Parker is not escaping toward another star at that full speed. Much of its velocity comes from falling deep into the Sun's gravity and following a tightly controlled orbit. Even if a future probe departed the solar system at several hundred kilometers per second, Proxima Centauri would remain thousands of years away. The fastest speed ever reached by a spacecraft does not automatically become an interstellar cruise speed. The mission must carry useful equipment while surviving acceleration, heat, radiation, and the long crossing. This is why many serious interstellar concepts begin by reducing mass as far as possible. A probe, weighing only grams, may be pushed to speeds that would be impossible for a crewed ship. But a gram-scale craft has little room for power systems, shielding, antennas, computers, and scientific instruments. It may reach the star quickly while struggling to return meaningful data. A large craft can carry more capability, yet its mass makes acceleration far harder. Make the spacecraft smaller, and it becomes easier to move, but harder to protect and operate. Make it larger, and it becomes more useful, but vastly more difficult to accelerate. It is small enough to have been launched with chemical rockets and gravity assists, but large enough to carry multiple instruments, power, antennas, and systems designed for decades of work. Rockets carry propellant, accelerate that propellant backward, and move forward in response. To reach a higher final speed, a rocket needs more propellant or a more efficient way to throw that propellant away. For missions inside the solar system, careful staging and gravity assists make this manageable. For interstellar speeds, ordinary chemical rockets become impractical long before the desired velocity is reached. A spacecraft cannot carry enough conventional fuel to accelerate a useful payload to thousands of kilometers per second. They used powerful rockets, precise navigation, and rare planetary alignments. And they remain tens of thousands of years from crossing the distance to the nearest star. The result is a silent object drifting outward, while the destination remains almost unchanged in the sky. The spacecraft carries a golden record, containing sounds, music, images, and greetings from Earth. It was created as a message for an uncertain future, attached to an object that may outlast the civilization that launched it. Its metal may survive while continents change, and the Sun moves through distant parts of its galactic path. To study Proxima Centauri directly, the probe must reach the system while its instruments function, and while Earth still has the ability to receive the signal. A journey lasting 75,000 years would return data to a species, planet, and technological culture impossible to predict. The scientists who designed the mission would be separated from the result by more generations than recorded history contains. A civilization could launch the probe as an act of faith, but it could not operate the mission in the way space agencies operate missions today. A spacecraft reaching Proxima within 20 or 40 years could send results back to people who remembered the launch. A journey lasting 200 years might still connect institutions across generations. A journey lasting tens of thousands becomes archaeology sent into the future. The failure belongs to the comparison between spacecraft speed and stellar distance. The probe is doing exactly what physics allows at the velocity it was given. To change the outcome, a future spacecraft must leave the solar system far faster than Voyager. It cannot rely only on another planetary alignment or a slightly larger chemical rocket. The increase must be large enough to shorten tens of thousands of years into centuries, decades, or less. That means changing the amount of energy placed into the spacecraft by orders of magnitude. And once Voyager's historic journey had shown how little progress even decades of motion could make toward the nearest star, the question was no longer whether a spacecraft could keep moving, but how any engine could give it enough energy to make that movement matter. Every interstellar journey imagined with known physics must somehow place an enormous amount of energy into a relatively small object and turn that energy into controlled motion. The spacecraft must be accelerated, guided, protected, and eventually slowed, while carrying every system needed to survive the crossing. A spacecraft coasting through the vacuum does not need fuel to maintain its motion, but reaching that motion requires work. The faster the craft must travel, the more energy must be transferred into it before the long cruise can begin. Doubling speed feels like it should require roughly twice the effort. But kinetic energy grows with the square of velocity. If the speed doubles, the energy becomes 4 times larger. If the speed increases by a factor of 10, the energy becomes 100 times larger. This change is easy to overlook because everyday vehicles lose so much energy to friction, air resistance, and heat. On Earth, fuel is used constantly just to maintain speed. Once resistance is removed, the energy required to accelerate the spacecraft remains stored in its motion. A faster vehicle is not merely moving more quickly. It carries far more kinetic energy, and that energy must come from somewhere. A probe traveling at 1,000 kilometers per second would move almost 60 times faster, but it would carry thousands of times more kinetic energy for the same mass. A spacecraft moving around 30,000 kilometers per second would cross the distance to Proxima Centauri in several decades, ignoring acceleration and braking time. This is the kind of speed that begins turning interstellar travel into a mission connected to one human lifetime. A one-ton spacecraft moving at 10% of light speed would carry kinetic energy comparable to a vast industrial output concentrated into one moving object. A larger vehicle carrying people, shielding, life support, fuel, and scientific equipment would require far more. A spacecraft cannot be made from velocity alone. It needs structure, computers, instruments, power, communication, thermal control, and protection from radiation and dust. A crewed ship would need living space, water, air, food systems, medical equipment, redundancy, and materials strong enough to survive years or centuries of operation. A rocket moves by throwing mass backward. The faster and more efficiently the exhaust leaves, the more speed the spacecraft can gain. But the propellant must be carried from the beginning, unless it can be collected or supplied along the route. The engines burn that propellant and expel hot gas at high speed, producing thrust. This method is powerful enough to lift spacecraft from Earth and send probes across the solar system. It is not powerful enough to accelerate a useful interstellar vehicle to a significant fraction of light speed. Chemical reactions release only a limited amount of energy compared with the rest mass of the fuel. They can produce exhaust velocities measured in a few kilometers per second. Interstellar missions require final spacecraft speeds thousands of times greater than that. The rocket must carry enough propellant to accelerate not only the payload, but also the unburned propellant that will be used later. Early in the flight, the engine is pushing almost the entire future mission. This is why rockets use stages. Empty tanks and engines are discarded, so later stages do not need to accelerate useless structure. But an interstellar chemical rocket would need an absurd number of stages, or an impossible quantity of propellant. Even if a chemical rocket could be assembled in space, away from Earth's gravity, the energy inside its fuel would remain too small. The spacecraft must still turn stored chemical energy into a velocity that is far beyond the exhaust speed of the engine. A rocket works best when its exhaust leaves much faster than the final speed demanded from the craft. When the desired spacecraft speed greatly exceeds the exhaust velocity, the required propellant grows exponentially. A small increase in required velocity can demand a large increase in fuel. At interstellar speeds, the numbers quickly stop describing a practical vehicle. It is that almost all of the mission becomes propellant needed to accelerate more propellant. A fission reactor can release millions of times more energy per kilogram than ordinary combustion. Nuclear thermal engines could heat propellant to much higher temperatures than chemical rockets, producing faster exhaust. Other concepts would use nuclear explosions, pulsed propulsion, or electric systems powered by reactors. Trips to Mars could become shorter. Heavy cargo could move more efficiently. Probes might reach the outer planets and nearby interstellar space faster than Voyager. Yet most nuclear fission designs still fall far short of the speed needed for a practical journey to Proxima Centauri. That is a remarkable improvement in engineering terms, but still far beyond the lifespan of a spacecraft, a crew, or a scientific institution. Fusion is the process that powers stars, combining light atomic nuclei and releasing part of their mass as energy. A fusion engine could, in principle, produce much faster exhaust than chemical or ordinary fission propulsion. Some interstellar studies have imagined enormous unmanned probes driven by repeated fusion reactions. The vehicle would carry vast quantities of fuel, often in the form of hydrogen isotopes or other light elements, and use the released energy to accelerate exhaust backward at extreme speed. This could reduce the journey to Proxima from tens of thousands of years to decades or centuries, depending on the design. Humanity can create fusion reactions, yet controlled fusion power itself is still developing. A compact, reliable engine able to operate in space for years while producing interstellar-level thrust does not exist. The fuel may need to be stored at extremely low temperatures or formed into countless precisely delivered pellets. The engine must handle intense radiation, heat, magnetic fields, and repeated reactions without destroying itself. Even if those problems are solved, a fusion spacecraft would likely be enormous. Constructing such a craft would require an industrial system in space far beyond anything currently available. Materials would need to be mined, processed, assembled, tested, and launched without depending on one fragile structure lifted from Earth. Most of it could exist only to hold fuel, radiators, shielding, engines, and the structure needed to keep them aligned. When matter and antimatter meet, their mass can be converted almost completely into energy. In principle, this makes antimatter one of the most powerful fuels allowed by known physics. This has made antimatter propulsion a common part of serious speculation about interstellar flight. It must be created, and producing it requires at least as much energy as it later releases, with real processes losing much more. The total amount ever produced is far below what even a small interstellar mission might require. Antimatter cannot touch ordinary matter. It must be held inside electromagnetic fields in an extremely controlled vacuum. A spacecraft carrying a useful amount would need containment systems operating without interruption through launch, acceleration, and years of travel. Antimatter may be physically possible, but practical production and storage remain far beyond current capability. Greater energy density reduces fuel mass, but it also increases radiation, heat, containment risk, and the consequences of failure. An interstellar engine must release energy fast enough to accelerate the ship, yet gently enough to avoid destroying the ship around it. They must remain cool enough to function while sitting near a propulsion system, releasing extraordinary energy. Every kilogram added to solve one problem increases the energy required to solve the original problem. External energy might accelerate it without requiring the craft to carry its own fuel. A laser could push a light sail, allowing the heavy power source to remain near Earth. This idea changes the rocket equation, because the spacecraft no longer carries the machinery or propellant producing the initial acceleration. A powerful laser array would need to deliver vast energy without damaging the sail or losing too much light around it. The probe may accelerate rapidly, but it must survive forces far stronger than those experienced by ordinary spacecraft. A crewed ship could not be pushed in the same way without a laser system and sail of almost unimaginable scale. The smaller probe can carry less shielding, less power, and a weaker transmitter. A civilization would need to build the laser array, power it, control it, and aim it with extreme accuracy. The beam would push the sail for minutes or hours, but a tiny pointing error could send the probe far from its target after 4 light-years of travel. If no braking system existed at Proxima, it would pass through the system at the same enormous speed. The very energy that makes arrival possible would also make staying impossible. The mission must include acceleration distance, cruise time, course corrections, shielding, communication, and deceleration. A design that solves one stage while ignoring the others may produce a fast object rather than a useful spacecraft. Humans can tolerate only limited forces for extended periods. A tiny robotic probe may survive thousands of times Earth's gravity during a laser launch. To protect passengers, acceleration may need to continue gently for months or years. Gentle acceleration creates a long powered phase and demands an engine that works reliably across that time. A mission accelerating at a comfortable rate could eventually reach high speed, but the total energy remains unchanged. At 10% of light speed, ordinary formulas remain useful with modest corrections. At half the speed of light, relativistic effects become much more important. At speeds close to light, a crew might experience a shorter journey than people remaining behind. But reaching those speeds requires energy approaching impossible levels for a massive ship. That makes the destination seem almost reachable compared with the rest of the galaxy. Yet those percentages still demand technologies far beyond present spacecraft. The required energy may need to come from a large fraction of a nation's electrical production, a planet-wide network, or an industrial system built around the sun. The spacecraft might be small, but the infrastructure behind it could be enormous. The mission would represent not one rocket, but an entire technological ecosystem. There may be no single tower, flame, or dramatic moment when a starship rises from Earth. The spacecraft could be assembled in orbit, accelerated by distant machines, and leave the solar system as a tiny moving point. A heavier probe carries better instruments and stronger communication systems. The design becomes a negotiation between everything the mission wants to do and everything propulsion allows it to carry. The nearest star is difficult because no part of the spacecraft can be designed in isolation. A larger rocket, a gravity assist, a solar sail, or a close pass near the sun can add velocity. It is gaining enough speed to reduce 75,000 years to something meaningful, while carrying a vehicle that can still function when the acceleration ends. It requires a propulsion system with far greater energy density, an external power source of immense scale, or a spacecraft so small that much of what normally defines a mission must be removed. The energy can be reduced only by reducing mass or accepting a slower journey. And even if a future engine could pay that cost and push a spacecraft across the darkness at a meaningful fraction of light speed, the mission would still face the problem hidden at the far end of every acceleration: finding a way to stop. And once the energy needed to reach interstellar speed had turned every kilogram, fuel tank, shield, and engine into part of the same growing problem, the journey could no longer be understood without confronting the even harder task of slowing down at the destination. A spacecraft can cross the distance to Proxima Centauri at extraordinary speed and still fail to reach the system in any meaningful sense. If it cannot slow down, the destination becomes only a brief interruption in a journey that continues into deeper space. At 10% of light speed, the craft would travel around 30,000 kilometers every second. It could cross the distance between Earth and the Moon in little more than 12 seconds. It could pass the entire diameter of the Sun in under a minute. A planetary system that took years to approach would disappear behind it almost immediately. Proxima Centauri is a small red star, and any planets around it orbit within a compact region compared with the wider solar system. A probe arriving at interstellar speed might have only hours to gather its most valuable observations. A camera would need to turn quickly. Instruments would need to identify targets, collect data, protect themselves from radiation, and store the results while the geometry changed faster than most space missions have ever experienced. The spacecraft would not circle back naturally. Its path would carry it out of the system, and the star would begin fading behind it almost as soon as it became large enough to study. Even a short visit might provide close images of Proxima, measurements of its magnetic activity, and direct observations of any planets along the route. A probe passing near Proxima b could examine its atmosphere, search for signs of water, and test whether the planet is protected from the star's powerful flares. Images can blur. Pointing becomes harder. Communication begins only after the encounter has already ended. The probe may travel for decades to reach the system and experience its destination in a period shorter than an ordinary day. A ship approaching another star is usually shown slowing into orbit, studying the planets and choosing where to go. A spacecraft arriving at 30,000 kilometers per second keeps moving at 30,000 kilometers per second unless something removes its energy. The same energy placed into the spacecraft at departure remains stored in its motion during arrival. A rocket can do this by turning around and firing its engines in the opposite direction. The exhaust carries momentum away, reducing the craft's forward speed. It is also one of the worst possibilities for a mission already struggling with mass. If the spacecraft carries all the fuel needed for braking, that fuel must be accelerated from the solar system at the beginning. The departure engine must push the payload, the structure, the shielding, and the propellant that will remain unused for decades. A spacecraft that can reach 10% of light speed may need nearly the same change in velocity to stop. The mission does not require one enormous acceleration. It must slow at Proxima, accelerate away from Proxima, cross the distance home, and slow near the Sun. The energy and propellant requirements can become so extreme that a return journey stops being a realistic part of the design. The earliest interstellar missions may therefore be one-way even when they carry only machines. But if it cannot brake, even the one-way mission becomes a flyby rather than an extended exploration. A tiny laser-driven probe may be accelerated from the solar system by an external beam and sent toward Proxima at a significant fraction of light speed. Because the probe carries little or no propulsion fuel, its mass remains low enough for the beam to push it rapidly. Once the craft is 4 light-years away, that launching system cannot simply pull it backward. A second laser array near Proxima would solve the problem, but no infrastructure exists there. Building such a system would require an earlier mission that had already reached the star and survived long enough to construct it. The sail could be angled so that photons from the star push against the direction of travel. The nearby Alpha Centauri stars might also contribute if the trajectory were designed carefully. The force builds gradually and depends on the sail's size, mass, reflectivity, and path. A craft arriving too quickly may pass through the useful region before the light can remove enough speed. The sail must survive decades of travel and remain precisely shaped when it is finally needed. It may also need to pass dangerously close to one or more stars to receive enough braking force. The sail that remained cold and folded through interstellar darkness may suddenly face a bright environment while moving at thousands of kilometers per second. A small error in angle could turn braking into acceleration or send the probe away from the desired planet. The approach would need to be planned years earlier and executed without real-time control from Earth. A magnetic sail could create a wide field around the spacecraft and interact with charged particles in the interstellar medium or stellar wind. Instead of striking a solid surface, incoming particles would be deflected by the magnetic field, transferring a small amount of momentum to the craft. The surrounding medium is extremely thin, so the magnetic field may need to extend across a very large area. Power, superconducting materials, cooling, and control systems would have to operate reliably for decades. A system large enough to brake effectively adds mass, while mass increases the amount of momentum that must be removed. The concept offers a path around carrying ordinary propellant, yet it does not make stopping easy. A related design could use electric fields to deflect protons in the surrounding plasma. The details differ, but the principle remains the same. Allow the spacecraft to push against the thin material already present between the stars. This is attractive because the craft would not need to carry every reaction mass from Earth. But the low density that makes interstellar space feel empty also limits how quickly momentum can be transferred. Its trajectory would become a long, controlled descent, rather than one sudden maneuver. If it begins too early, the total journey becomes longer, and the spacecraft must survive active operation for more time. A probe might accelerate with a laser sail, coast through interstellar space, then deploy a magnetic sail during the later part of the journey. Small thrusters might make course corrections and guide the craft toward a chosen planet. A mission that began as a tiny probe can slowly become complicated enough that the original acceleration method no longer works as expected. The spacecraft becomes more capable, but each improvement makes it harder to move. Its designers may need to choose between a fast flyby with better travel time and a slower mission capable of entering orbit. The orbital mission might take far longer or require a propulsion technology not yet demonstrated. The slower mission can observe more carefully if it survives long enough to arrive. Proxima Centauri and the brighter Alpha Centauri pair are part of the same broad stellar system, but they are separated by large distances. A probe that breaks near Proxima would not automatically gain easy access to Alpha Centauri A and B. Travel between them could require years or decades, depending on the final speed and route. It creates several possible targets distributed across a moving stellar neighborhood. Should it enter orbit around the star, around a planet, or simply remain inside the system long enough to observe? If a spacecraft passes a planet at thousands of kilometers per second relative to it, the planet's gravity cannot capture the craft into a stable orbit. The probe must reduce its relative speed to something the local gravity and propulsion system can manage. The spacecraft must reach the same place while moving in nearly the right direction and at a compatible velocity. A target only slightly missed after 4 light-years could remain millions of kilometers away. A target reached at the wrong speed could vanish behind the craft before the instruments finished adjusting. The position and motion of Proxima can be measured accurately, but the planets around it are harder to predict over decades. Orbital models improve as observations continue, yet small uncertainties can grow. The probe may need to update its route using its own cameras and sensors during the final approach. By the time a signal describing the approaching system arrives here, the spacecraft will already be more than 4 years farther along in its own timeline. The probe must recognize the star, locate the planets, choose corrections, and protect itself without waiting for approval. At 10% of light speed, the spacecraft covers 1 astronomical unit in less than an hour and a half. A system designed on Earth must respond to an environment no human has seen directly. The craft may discover additional planets, dust belts, or magnetic conditions that were unknown at launch. It must carry rules flexible enough to adjust without turning a small uncertainty into mission failure. A probe that slows near Proxima can point its antenna toward Earth for years, gather data, and transmit repeatedly. Its antenna must maintain alignment while the craft travels through the system and into deeper space. The probe's small power source must send information across 4 light-years to receivers capable of separating it from noise. A tiny spacecraft may collect extraordinary images and fail to deliver them because its transmitter is too weak. Laser communication could concentrate energy into a narrow beam, making better use of limited power. But the beam must be aimed with extreme precision toward the future position of the solar system. Earth, the Sun, and the receiving telescopes will have moved during the 4 years the message spends in transit. The spacecraft must know where its signal will arrive, not merely where Earth appears at the moment of transmission. A mission that enters a long orbit could observe stellar flares, changing planetary atmospheres, seasons, and magnetic activity over years. Without that control, the spacecraft is still traveling even while the destination passes around it. A robotic probe can survive a high-speed flyby and send back whatever data it collects. People would need time to study the system, choose a safe location, establish orbit, and prepare for conditions that may differ from every prediction made before launch. The crew would depend on the engine not only to arrive, but to avoid being carried permanently into the darkness beyond the star. A failure during braking near Proxima would occur more than 4 light-years away. The mission would have spent decades crossing interstellar space, only to discover that arrival depended on machinery used near the very end. An engine kept inactive during most of the journey would need to work perfectly after years of radiation, cold, and microscopic impacts. Valves, magnets, fuel systems, sails, or field generators could not be tested under the exact destination conditions until they were already needed. A braking system strong enough to save the mission can make departure harder. A lighter vehicle can accelerate more easily, but has fewer backups. Departure occurs near Earth, surrounded by instruments, engineers, repair systems, and the accumulated knowledge of the solar system. The destination is distant, only partly understood, and already years beyond direct help. The craft must remove an enormous amount of energy using equipment that has survived the entire journey. For a human ship, the failure could remove every possibility of survival at the destination. The nearest star, therefore, demands 2 interstellar vehicles hidden inside one spacecraft. The other must be capable of turning that fast-moving object into a controlled explorer near Proxima. They share the same mass, structure, and power, but their tasks oppose each other. Only when both succeed does the journey become more than a line drawn between 2 stars. And once arrival had revealed itself as a second interstellar journey hidden inside the first, the question could no longer remain only how to move a spacecraft, but whether human life could survive everything the crossing would demand. A machine can be powered down, protected behind shielding, and awakened near the destination. A human body cannot be stored so easily. From the moment a crew leaves Earth, the spacecraft must become an artificial world. It must provide breathable air, clean water, food, stable temperatures, light waste removal, medical care, and protection from an environment that offers none of these things naturally. The difference is not simply a longer supply list. Carrying enough bottled oxygen, drinking water, and packaged food for an interstellar crossing would make the ship impossibly heavy. The crew would need to reuse almost everything. Water from breath, sweat, washing, and waste would have to be collected and purified again. Carbon dioxide would need to be removed from the air, while oxygen was continually replaced. Nutrients contained in waste might need to return to food production rather than being sealed away. The spacecraft would function less like a vehicle and more like a closed ecosystem. An interstellar ship would have no supply vehicle approaching every few months. A filter that slowly lost efficiency could not simply be replaced from a warehouse on the ground. A pump, valve, seal, sensor, or computer might need to function for longer than any complex machine has ever operated. The crew would have to carry spares, manufacture new parts, or redesign damaged systems while moving through deep space. Yet without backups, one small failure could threaten the entire population on board. A broken water processor would not be an inconvenience. It could place a deadline on survival. The same closed environment that preserves life would also concentrate every mistake. A toxic chemical released into the air would remain inside the ship until another system removed it. A pathogen could move through a crew that had nowhere else to go. Mold and bacteria could grow in hidden surfaces, pipes, and insulation. Inside a starship, life would depend on a limited volume of machinery. The ship would need to understand its own environment constantly. Thousands of sensors might watch oxygen, carbon dioxide, humidity, pressure, temperature, microbes, and trace chemicals. Food creates a deeper challenge because it must remain useful across time. A ship crossing interstellar space would probably need to grow part or all of its food. Every plant requires light, water, space, controlled temperatures, and a stable nutrient supply. Crops can fail, diseases can spread, seeds may not germinate as expected after long storage. A harvest lost between stars may leave no recovery beyond the reserves already on board. Human beings can survive on repetitive meals for a time, but a community living for decades would need nutrition that supports physical health and enough choice to protect morale. Every meal would connect agriculture, water recovery, waste processing, energy use, and the emotional condition of the crew. Radiation would reach through all of these systems. Earth's atmosphere and magnetic field protect life from much of the high-energy radiation moving through space. Once a ship travels far from the planets and the sun's protective environment, the crew would face galactic cosmic rays and energetic particles produced by stellar activity. The damage can build quietly inside cells, Long exposure may increase cancer risk, harm the nervous and cardiovascular systems, affect vision, and create other changes that remain difficult to predict across an interstellar lifetime. Shielding helps, but effective shielding is heavy. Water, fuel, food, and structural materials could be arranged around living areas so that mass already needed for the mission also protects the crew. Adding more mass improves protection only up to a point while making acceleration and braking harder. The ship must be light enough to travel and heavy enough to keep its passengers alive. A slower journey increases total radiation exposure. A faster journey reduces the years spent in space but demands greater energy and turns dust impacts into more serious hazards. Gravity creates another uncertainty. Human bodies evolved under the constant pull of Earth. In weightlessness, bones lose density, muscles weaken, fluids shift toward the head, balance changes, and the cardiovascular system no longer works against gravity in the familiar way. Exercise can reduce some of these effects, but it does not recreate every condition of life on the ground. That experience is valuable, but an interstellar crew might spend an entire lifetime away from a natural gravitational field. No one knows with confidence how pregnancy, early development, growth, and aging would proceed across generations in low gravity. Artificial gravity could be created by rotation. A large ring or cylindrical habitat could spin, pressing people toward the outer surface and producing a force that feels similar to gravity. A larger ring reduces these effects but adds structure, mass, bearings, and complex mechanical demands. But every arrangement would need to function for a length of time never tested. Medical care would also change beyond recognition. A starship could carry medical equipment and highly trained crew members, but it could not carry every specialist or treatment. Communication with doctors on Earth would be delayed by years. A medical emergency would begin and end long before outside advice arrived. The crew would need to diagnose and treat cancer, infection, injury, dental problems, mental illness, pregnancy complications, and chronic disease with the people and equipment already on board. It would carry part of a civilization's medical knowledge and the means to apply it without help. The composition of the crew would matter as much as the machinery. A small group is easier to support because it needs less food, living space, and shielding. But too few people create social and biological risks. A larger population is more resilient, but every additional person increases mass and resource demand. A voyage lasting 200 years would likely require children to be born on board and inherit a mission they never chose. The people who arrive would not be the people who left Earth. The destination would exist as a promise passed through families, records, training, and stories. Children raised between stars might question why their entire world was moving toward a place selected by people who died before they were born. The ship would need laws, education, conflict resolution, work, privacy, culture, and some way to change without losing the knowledge required for arrival. A society cannot remain unchanged for centuries simply because its founders wrote instructions. They would need to teach every generation why the life support system works, how the engines are repaired, what dangers lie outside, and what must happen near Proxima. The mission would need living traditions of engineering, medicine, agriculture, and navigation. People would have to understand systems created long before their birth and preserve them for people they would never meet. The crew would also live inside extreme confinement. Even a large spacecraft would contain far less space than a town on Earth. The same corridors, rooms, faces, and sounds would repeat year after year. There would be no natural weather, distant landscape, or open horizon. Isolation would make small social problems dangerous because every person would remain part of the same life-supporting system. Depression, distrust, grief, boredom, and exhaustion could reduce attention and cooperation. A community that lost confidence in the mission might stop maintaining it carefully. The ship would need spaces for solitude, recreation, exercise, art, education, and rituals that give time a human shape. People would need celebrations, rest, personal goals, and reasons to care about a future hidden beyond their own lifetime. If human metabolism could be slowed safely, passengers might consume fewer resources and experience less of the journey. But no method currently allows healthy humans to sleep for years and wake without serious damage. The body still requires circulation, nutrition, waste removal, temperature control, and protection from radiation. Muscles and bones could weaken even more during prolonged inactivity. An automated medical system would need to watch each passenger continuously and respond to problems without waking a full crew. Suspended animation may reduce the experience of time, but it does not remove the need to preserve life through it. Embryos or genetic material could reduce mass further. A robotic ship might carry frozen embryos and attempt to create a human population near the destination. Yet this idea replaces one impossible responsibility with another. Machines would need to manage development, birth, infant care, education, emotional attachment, and the creation of a functioning society without adult humans present at the beginning. The mission might transport biology while failing to transport humanity. A living crew carries culture, judgment, compassion, and the ability to improvise. Those qualities are difficult to store in a tank. The more closely the mission is examined, the more the spacecraft begins resembling a small planet. It needs cycles of air and water, agriculture, waste processing, stable energy, shelter, medicine, education, and a society able to survive its own internal pressures. Earth provides these through systems spread across oceans, soil, atmosphere, ecosystems, and billions of people. A starship would compress them into one artificial structure, moving through darkness. There would be no second environment waiting beyond a damaged wall. Outside lies vacuum, radiation, and temperatures that cannot support an unprotected human body. The ship would not merely carry life, it would define the complete boundary of the living world. This makes reliability different from anything used on Earth. A bridge can close for repair. A power station can shut down while another supplies electricity. A damaged city can receive help from elsewhere. The essential systems of an interstellar ship cannot all stop at once. Maintenance must occur while people continue breathing, drinking, eating, and producing waste. The crew would repair the world from inside the world. A serious accident could force them into smaller protected sections, while damaged areas were isolated. Fire would be especially dangerous. Smoke and toxic gases would remain trapped in the enclosed atmosphere. Water used to control flames could damage electronics and reduce reserves. A rupture might cause pressure loss and require immediate sealing. The ship would need compartments, emergency shelters, and multiple independent systems, so one failure did not spread everywhere. Redundancy makes survival more likely, but the additional structure makes propulsion harder. The same argument that limited the engine returns inside the habitat. Human life requires mass. Water, shielding, food systems, medical equipment, living space, and spare parts cannot all be reduced to nothing. A tiny probe may cross interstellar space within decades. A human world cannot be made tiny without removing the conditions that make long-term survival possible. This may be the greatest difference between sending a machine and sending people. A probe can be designed around one purpose and accept a high risk of failure. A crewed ship must support thousands of ordinary needs every day of the voyage. The mission cannot be successful only at launch and arrival. It must succeed continuously. Every breath becomes part of the journey. Every glass of water depends on a cycle that must never quietly collapse. Every generation must receive a working world from the one before it. And even if the ship maintained its air, water, gravity, food, medicine, and social order for the entire crossing, the crew would still be moving farther from every person, institution, and source of help that remained on Earth. And once the spacecraft had become a complete artificial world, whose survival depended on systems and people that could never afford to fail, the distance to Proxima Centauri would reveal its most isolating truth. No rescue could follow them into the darkness. At the beginning of the journey, Earth would still feel close. Messages would take only seconds or minutes to arrive. Engineers could monitor the ship, doctors could review medical data, and families could speak with the crew with only a short delay. But the delay would grow with every kilometer. Far beyond the planets, a complete exchange could consume hours. Years later, the crew might send a question and continue living long before the answer returned. The silence would not come from damaged equipment alone. It would be built into the distance. Radio waves and laser signals travel at the speed of light, the fastest speed available to information. Better antennas could make the signal clearer, and stronger transmitters could make it easier to detect, but nothing could make the message arrive early. Halfway to Proxima Centauri, a transmission would need more than 2 years to reach Earth. A reply, sent immediately, would need more than 2 additional years to return. The crew could ask for help and receive an answer. 4 years later. By then, the problem might no longer exist in the same form. A damaged reactor would already have been repaired, abandoned, or lost. A medical emergency would already have ended, and navigational choice would have carried the spacecraft far beyond the point where the question was asked. Earth could provide knowledge, but rarely action. The crew would still send reports. Scientists could study the data and offer advice for slow problems. Families could record messages. Mission teams could preserve a connection across the years. Yet it would no longer feel like conversation. Each transmission would resemble a letter sent into another time. A crew member could send a recording to someone on Earth and die before the reply reached the ship. The signal would continue crossing space after the person who created it was gone. Earth would hear the spacecraft's past, while the crew received a version of Earth that had already moved on. Neither side would know the other in the present. Near Proxima Centauri, the one-way delay would exceed 4 years. A message announcing arrival would not reach Earth until the spacecraft had already spent years inside the system. Humanity might celebrate the planned arrival date, while still having no proof that the ship survived. Modern spacecraft are operated by large teams spread across the planet. Engineers examine telemetry, simulate failures, and send carefully prepared commands. Specialists who never leave Earth contribute whenever an unusual problem appears. An interstellar ship could not depend on that kind of support. Its crew and onboard systems would need enough knowledge to replace much of a planet. A failure in the power system might require electrical engineers, materials specialists, programmers, and people who understood components built generations earlier. A medical emergency might demand surgery, diagnosis, pharmacy, and psychological care. A damaged food system could involve plant biology, chemistry, plumbing, and microbial control. Earth could send information. The information would arrive too late for urgent situations. The spacecraft would need to detect problems early, compare them with stored knowledge, test possible solutions, and act without waiting for approval. Autonomy would become one of the main survival systems. Artificial intelligence could help by monitoring thousands of sensors, searching technical records, and simulating repairs. But it would live inside the same closed world as everything else. Its sensors could fail, its models could be incomplete, its software might face conditions never imagined before launch. The crew could not treat it as an infallible voice. A ship dependent on one central intelligence would carry a single point of failure at the center of its society. A ship without powerful automation might bury its crew beneath constant maintenance and alarms. The balance would need to survive for decades. Many failures would begin quietly. A seal could leak too slowly to notice at first. A toxic chemical could build in the air. A slight navigational error could grow while Proxima remained only a point of light. By the time the danger became obvious, the easiest moment to correct it might have passed years earlier. Navigation would be especially unforgiving. The stars could provide direction, and the spacecraft could measure its motion. But the destination would continue moving through the galaxy. The route calculated near Earth would need regular correction. Tiny forces would accumulate. Dust and gas would strike the ship. Radiation could affect instruments. Small imperfections in propulsion could shift the course. A deviation too small to matter near the Sun could become an enormous miss after 4 light years. Earth could not notice the mistake and correct it in real time. The spacecraft would have to compare the observed positions of stars, update its own path, and make corrections independently. Near Proxima, the pace would suddenly increase. The target system would begin changing rapidly in the instruments. Planets would move through their orbits. Dust, magnetic fields, and stellar activity could alter the expected approach. A fast probe might have only hours to react. A crewed ship attempting to brake would depend on decisions made before Earth could see the same conditions. Arrival would be controlled entirely by people and machines already there. For the original crew, Earth would remain a place remembered directly. Its weather, oceans, cities, and ordinary sounds would belong to personal memory. For people born on board, Earth could become something known through recordings and stories. They would receive messages from a planet they had never visited and might never be able to reach. The delay would make Earth feel less like a distant home and more like another civilization connected through history. The cultures of the ship and Earth would change separately. Language would shift. New traditions would form. Technologies developed on Earth might be described in messages, but impossible to reproduce with the ship's limited materials. After a century, the two societies could understand each other, while no longer sharing the same daily reality. A generation born halfway to Proxima might question why every major choice should be reported to people whose replies arrived years later. Earth might see the ship as a historical project rather than an active community. Eventually, the link might survive mainly through scheduled reports and personal archives. The spacecraft would remain physically connected to humanity by radio, while becoming socially independent. That independence would not necessarily destroy the mission. Human communities can adapt to isolation and create meaning inside limited environments. The crew could build art, education, ceremonies, work, and institutions suited to life between stars. They might stop viewing the ship as a temporary prison and begin treating it as their world. But this adaptation would make arrival more complicated. A community shaped entirely by the spacecraft might not welcome the destination in the way the founders expected. Proxima Centauri could represent danger, uncertainty, and the loss of the only environment many passengers had ever known. The ship, despite all its limits, would be familiar. Its gravity, light cycles, air, food, and social spaces would define normal life. A planet around another star would be unknown. Landing could expose the crew to unfamiliar gravity, chemistry, weather, radiation, and surface conditions. Some passengers might prefer to remain on board or in orbit. The mission could arrive after generations of sacrifice and discover that the safest home available was still the ship. This possibility changes the meaning of rescue. At departure, rescue means another spacecraft sent from Earth. Later, it could mean returning to the artificial world after a dangerous attempt to settle a planet. But no second ship would be nearby. If the habitat failed during the crossing, Earth could not reach it. A rescue craft launched after receiving a distress signal would face the same enormous distance and arrive far too late. Even a much faster mission could not reverse an immediate disaster. A serious failure would not begin a rescue operation. It would begin a local struggle for survival. The people responding to an emergency would be the same people threatened by it. A fire team could not evacuate to another town. Doctors could not transfer a patient to a better hospital. Engineers could not order a replacement machine from a factory. The ship would contain every available layer of help. If those layers failed, nothing remained behind them. This would make prevention more important than dramatic rescue. The community would depend on quiet maintenance, repeated inspections, and a culture willing to treat small problems seriously. Children might learn emergency procedures alongside ordinary education. Every adult could carry more than one technical role so that knowledge survived illness, conflict, or death. The ship would become a society organized around continuity. Yet perfect preparation is impossible. A material could fail in a way never seen during testing. A collision could damage a region believed to be protected. A disease could develop inside the closed environment. A solar event could exceed every prediction. The crew would need to improvise with whatever remained on board. A damaged system might be repaired using components taken from equipment considered less important. Rooms could become workshops. Scientific instruments might be dismantled to support life support. Over time, the ship could change from its original design. The vessel arriving at Proxima might look very different from the one that left Earth, with its history visible in every repaired surface and replaced machine. Its scientific equipment could also become outdated during the crossing. Earth might send improved software and new methods, but it could not transmit new hardware. A telescope built at launch could survive long enough to arrive while being primitive compared with instruments created decades later. A faster probe launched later might even overtake the original mission. A civilization could launch a ship using the best technology available, then develop far better propulsion before that ship arrived. The later craft might reach Proxima first. The earlier crew could spend generations crossing a distance that a newer vehicle completed in years. But waiting forever means no mission begins. For a robotic probe, being overtaken would be disappointing, but not tragic. A human ship would carry lives shaped permanently by choices made before launch. The people on board would bear the cost of every assumption about propulsion, medicine, society, and the destination. The distance would freeze those assumptions into hardware. Once the craft traveled far enough, turning back would become no easier than continuing. Reversing course would require removing the same motion that carried the ship outward and creating it again in the opposite direction. The required fuel might not exist. The mission would pass a point where Earth was no longer a practical destination. After that, every problem would have to be solved while moving forward. For much of the journey, neither star would feel close. Earth would shrink into a delayed signal behind them, while Proxima remained a delayed image ahead. The spacecraft would be the only place in the universe capable of helping the people inside it. That may be the deepest isolation created by 4 light-years. The distance is small beside the Milky Way, but large enough to separate cause from response, danger from assistance, and one generation from the decisions of another. It turns communication into memory and makes independence unavoidable. Even perfect engines and life support would not restore the immediacy of Earth. The crew could carry its knowledge, voices, images, and history. They could not carry its oceans, hospitals, industries, or billions of people ready to solve unexpected problems. The journey would remove those layers one by one until only the spacecraft remained. And once the years of silence had placed the spacecraft beyond rescue, the nearest star could no longer be treated simply as a destination, because Proxima Centauri itself might offer an environment too hostile for the travelers who survive the journey. It is smaller, cooler, and far dimmer than the Sun, which at first can make it sound gentle. Red dwarf stars burn their fuel slowly and may survive for trillions of years, offering far more time than stars like the Sun. Proxima Centauri is magnetically active. Its surface can release powerful flares that brighten the star suddenly and send high-energy radiation into the surrounding system. Others release enough energy to transform the space around the star into a dangerous environment for any nearby planet. The planet completes one orbit in a little over 11 Earth days and lies only a small fraction of the distance that separates Earth from the Sun. Proxima is much dimmer than our star, so a planet must orbit close to receive enough warmth for liquid water to be possible. A habitable zone describes a range of distance where the temperature might allow liquid water on the surface of a planet under suitable conditions. It does not prove that the planet has an atmosphere, a stable climate, a magnetic field, or any protection from its star. For Proxima b, the same close orbit that provides warmth also places the planet directly inside the activity of a flaring red dwarf. High-energy ultraviolet and X-ray radiation can heat the upper atmosphere of a planet and help gases escape into space. Charged particles from the star can strike the atmosphere and slowly remove it, especially if the planet lacks a strong magnetic field. Atmospheric loss can continue quietly over millions or billions of years, molecule by molecule, until the surface becomes exposed to space. Models have shown that an Earth-like atmosphere placed in Proxima b's orbit could be removed far faster than Earth loses its own. The exact outcome remains uncertain because the planet's magnetic field, original atmosphere, interior, and history are unknown. A powerful magnetic field might reduce part of the loss, though it would not guarantee complete protection. The planet may have formed with much more water than Earth and retained some despite the star's activity. One version of Proxima b has an atmosphere, clouds, and areas where liquid water remains stable. A crew traveling 4 light-years would not know with certainty which world awaited them until observations had improved greatly or the ship approached the system. A destination chosen because it might support life cannot be treated as a guaranteed refuge. The spacecraft must remain capable of supporting its passengers even if every planet in the system is hostile. The ship that carried them across interstellar space may need to remain their home after arrival. A planet moving so close to a small star may become tidally locked, rotating once during every orbit so that the same side continually faces the star. Between them, a narrow region of constant sunrise or sunset could circle the planet. A thick enough atmosphere or ocean might transport heat from the bright side to the dark side, preventing one region from becoming too hot and the other from freezing completely. Clouds could gather above the warmest region and reflect part of the incoming light. But if the atmosphere were thin or absent, the temperature difference could become severe. The most stable conditions might exist only in selected regions, rather than across the full surface. Earth is habitable across many environments, yet even here, most locations are difficult for an unprotected human body. Deserts, polar ice, deep oceans, high mountains, and the upper atmosphere can kill quickly without technology. Proxima b could be technically habitable in a broad, scientific sense, while remaining impossible to settle without sealed habitats. Its gravity is also uncertain, because only a minimum mass is known with confidence from the way it pulls on its star. The planet is at least roughly Earth mass, but its true mass depends on the tilt of its orbit. Its surface might feel exhausting to people adapted to Earth, or to generations raised inside an artificial gravity habitat. The crew would need to adapt from the carefully controlled conditions of the ship to a natural environment whose pull might never feel familiar. The pressure could be too low for liquid water to remain stable, or so high that humans could not survive outside specialized suits. Even gases that are harmless in small amounts can become toxic at high concentrations. The surface could also contain reactive dust or chemicals capable of damaging lungs, seals, machines, and crops. Mars already demonstrates how a world can appear calm while its dust creates serious engineering concerns. Proxima b could present an environment no laboratory on Earth had reproduced completely. Proxima Centauri can produce flares far more energetic than ordinary activity from the Sun. During a strong event, ultraviolet radiation could rise rapidly. X-rays and charged particles could reach the planet soon afterward. A thick atmosphere might absorb part of the radiation, but repeated events could damage protective ozone or alter the planet's chemistry. Without an atmosphere, the surface would receive much more of the energy directly. A settlement might need to exist underground, beneath water, or behind heavy shielding. The crew could travel across 4 light years, only to build another sealed world hidden below the surface. Energetic particles may follow, depending on their speed and the magnetic conditions around the star. A settlement would need continuous monitoring and shelters ready for immediate use. Power grids, communication systems, electronics, and exposed equipment could all face repeated stress. Frequent smaller disruptions could slowly damage materials and make surface operations difficult. It could remain underground, underwater, or protected by chemistry unlike anything familiar on Earth. But conditions that allow microscopic life are not necessarily conditions that allow human beings to walk outside. A living planet could be scientifically priceless and ethically difficult to settle. Even simple organisms would represent a second origin of life, one of the most important discoveries in history. Local biology could interact with human bodies in unpredictable ways. Although organisms with an independent chemistry might not be able to infect us directly, a world capable of supporting life might be the one world they should avoid changing. A sterile world would remove that ethical problem but might offer fewer natural resources for survival. The mission could arrive needing water, minerals, and shelter, while trying not to damage the very evidence it crossed interstellar space to study. There is also the possibility that Proxima b does not pass in front of its star from Earth's viewpoint. Without a transit, astronomers cannot easily examine starlight filtered through its atmosphere. Future telescopes may separate the planet's own light from the star and search for atmospheric gases, surface conditions, or signs of climate. Even then, a distant spectrum will not answer every practical question faced by settlers. They would need a detailed environmental forecast for a world no human instrument had visited closely. Other planet candidates have been proposed, including worlds on wider orbits, though their existence and properties require continued confirmation. Some could offer water or raw materials without the same surface dangers as Proxima b. A crew might decide that living in space near the star is safer than landing on a planet. Habitats could remain mobile, moving away from dangerous regions and using shielding designed during the journey. The destination might become a new, space-based civilization rather than a planetary colony. The ship could enter a wide orbit, send robotic probes downward, and wait years before deciding whether any landing was safe. Such patience would require successful braking and life support capable of continuing indefinitely. The brighter Alpha Centauri A and B might offer other possibilities farther away within the wider stellar system. They resemble the Sun more closely than Proxima does, and planets around them could experience different conditions. But reaching them, after arriving near Proxima, would require another interstellar-scale journey compared with ordinary planetary travel. A mission designed for the nearest star might discover that the most promising destination lies far from the point it worked so hard to reach. Safety, resources, planetary conditions, and the ability to remain all matter equally. A slightly farther star with a calmer environment might be a better target, but every added light year increases travel time, energy, and communication delay. Humanity could spend centuries developing the ability to cross interstellar space and still find no nearby planet that welcomes human life. Earth has a stable surface, liquid oceans, a protective atmosphere, a magnetic field, moderate gravity, and a star calm enough for complex life to develop across billions of years. An interstellar journey could reveal that the true destination was not another Earth, but another place where machines could survive. The crew might live inside habitats forever, using local materials while remaining separated from the natural environment. In that case, reaching Proxima Centauri would expand civilization without ending its dependence on technology. The artificial world built for the crossing would become the foundation of life around another star. This outcome is less dramatic than stepping onto a green planet beneath an unfamiliar sun. It can offer scientific knowledge, energy, matter, and a new position inside the galaxy. A mission launched centuries from now would observe Proxima with instruments far better than those used today. Its planners might know the atmosphere of Proxima b, map its climate, and identify other planets before departure. Dust belts and small objects may remain invisible until the spacecraft approaches. Weather, surface chemistry, and local radiation could vary in ways too fine for distant telescopes to resolve. This is true of every exploration, but interstellar distance magnifies the consequence. A mission to Mars can change its landing site while remaining in communication with Earth. If the planet is worse than expected, the crew must adapt to using only the resources already present. The mission must be designed around failure before it knows what failure will look like. Tiny, fast spacecraft could pass through the system, photograph the planets, measure atmospheres, and report the radiation environment. Automated factories could prepare habitats or gather resources before people left the solar system. A probe launched today, even with a future system capable of reaching Proxima in 20 years, would not deliver its final results until nearly a quarter of a century after departure. The first human travelers might leave only after machines had studied the system for a century. The better humanity understands Proxima before departure, the less the crew must gamble with its survival. The crew, or the probe sent before them, must enter the system and discover which version of Proxima b is real. Proxima Centauri is not simply a red point waiting at the end of 4 light-years. It is an active star surrounded by an environment shaped by radiation, magnetic fields, moving planets, and a history that Earth can only reconstruct from faint signals. But before humanity can face those answers, it needs a method of crossing the distance that does not require a ship as massive as a world, or a voyage lasting longer than civilization. A machine can accept radiation that humans cannot, cross the system in a brief flyby, and return information without needing breathable air or a safe surface. The most realistic path toward Proxima may therefore begin with spacecraft far smaller than Voyager and far faster than anything yet launched. Their designs would trade the comfort of arrival for the possibility of reaching the star within one lifetime. And once Proxima Centauri had revealed that even the nearest destination might be a violent and uncertain place, the search for a way to reach it would turn away from larger starships and toward machines so small, light, and fast that they would barely resemble spacecraft at all. If the distance cannot be reduced, then the mass of the traveler must be. A heavy spacecraft needs enormous energy to accelerate. A tiny spacecraft needs less. The laws of motion do not become easier, but the scale of the engineering changes. This is why some of the most serious ideas for reaching another star begin not with a vessel carrying people, but with something closer to a thin sheet of reflective material attached to a miniature computer. A light sail moves without carrying ordinary fuel. Photons have no rest mass, yet they carry momentum. When light strikes a reflective surface, it transfers a tiny push. The force is weak, but in space it can continue acting without the sail needing to burn propellant. A much more powerful beam could push far harder. Instead of placing the engine on board, the energy source would remain near Earth. A large array of lasers could focus light onto a sail and accelerate the attached probe while the heaviest machinery stayed behind. The spacecraft would carry the motion without carrying the engine that created it. A rocket must accelerate its own fuel. A laser sail does not. Only the sail and the small probe need to cross the 4 light-years. If the spacecraft weighs only a few grams, an intense beam could push it to a significant fraction of light speed. The signal returning to Earth would need more than 4 additional years. A mission launched within 1 generation could therefore send information back, while some of the people who watched its departure were still alive. But shrinking the journey in time means shrinking the spacecraft almost beyond recognition. A gram-scale probe cannot resemble Voyager. There is no room for a large dish antenna, thick shielding, multiple heavy instruments, or a powerful reactor. Cameras, navigation systems, communication equipment, and computers would need to fit onto something comparable in mass to a small electronic device. During acceleration, the laser would need to remain focused on that sail while it moved away rapidly. A slight misalignment could push the probe away from Proxima Centauri or stop the acceleration too early. The sail would also need to remain stable. If it tilted, folded, overheated, or reflected the beam unevenly, the force could spin the spacecraft or tear the material apart. Even delicate electronics would need to survive the force without breaking free from the sail. The entire acceleration phase might last only minutes, yet those minutes would determine a journey lasting decades. There would be no ordinary engine on board to correct a major mistake. Small adjustments might be possible, but the route would mostly depend on the accuracy of the launch. The Sun would become another star behind it. Proxima would remain a point ahead. For the rest of the journey, the spacecraft would carry almost no ability to change the energy placed into it at departure. The darkness between the stars is not completely empty. Thin gas and microscopic dust remain scattered through it. At ordinary spacecraft speeds, these particles are a long-term concern. At 20% of light speed, they become a much more serious threat. Across 4 light-years, the spacecraft would encounter an enormous number of them. Shielding could protect the electronics, but shielding adds mass. A thicker front layer might absorb impacts while slowly eroding during the crossing. The probe could be shaped so that only a narrow edge faces forward, reducing the area exposed to collisions. Redundancy would exist across the fleet, rather than inside each spacecraft. Tiny probes could be sent in groups, perhaps hundreds or thousands, each following a slightly different path. Some would be lost during acceleration. Others might be destroyed by dust, suffer electronic failure, or miss the target. The mission would succeed through numbers rather than the reliability of one perfect machine. Yet every surviving probe would still need to know where it was. Navigation across 4 light-years demands precision, but all of this must occur with limited power and computing capacity. Memory would need to preserve software without corruption. A small craft cannot carry a large nuclear generator. Solar panels become nearly useless once the Sun is far behind, and Proxima remains too distant for most of the flight. The probe might rely on a miniature radioactive source, a long-lived battery, or energy stored at launch. Whatever system is chosen must remain useful after decades of cold and radiation. It must power navigation, instruments, data storage, and the transmission home. Communication may be harder than reaching the star. A probe could capture extraordinary images and still fail if it cannot send them across 4 light-years. Radio transmissions spread outward, becoming weaker with distance. A tiny antenna and limited power would produce a signal difficult to separate from background noise. Laser communication could concentrate the signal into a narrow beam, using energy more efficiently. But a narrow beam must be aimed with extreme accuracy. The probe would need to point toward the future location of the solar system while moving rapidly through Proxima's neighborhood. Telescopes could collect individual photons from the probe over long periods and slowly reconstruct the data. A modern space telescope can return vast datasets, but a gram-scale probe may be able to send only selected images and measurements. It could compress data, discard failed observations, and choose the clearest view of a planet without human guidance. At 20% of light speed, the probe would cross 1 astronomical unit in less than an hour. The region around Proxima where planets might orbit would pass quickly. Instruments would need to begin observing before closest approach and continue after the star was already behind. A planet could be hidden by the star, on the wrong side of its orbit, or too far from the planned path. Sending many probes at different times could improve the chance that at least one encountered favorable conditions. They would photograph, measure, transmit, and continue into deeper space. For a first mission, this may be enough. Humanity would see another star from nearby rather than from across light years. The probe could measure the density of interstellar gas, observe Proxima's surface, examine its flares, and search for the atmosphere of nearby planets. Even a few successful measurements would test ideas developed from distant observations. The mission would also reveal whether tiny spacecraft can survive relativistic travel. That experience could shape every interstellar design that followed. The method could produce far more thrust than ordinary engines and carry substantial payloads. Fusion-powered designs could accelerate unmanned probes to several percent of light speed, reducing the journey from tens of thousands of years to decades or centuries. Each idea attempts to solve the same relationship between mass, energy, and time. None of these ideas is forbidden by basic physics. The problem lies in the distance between a physical principle and a working machine. Laser arrays, large enough to accelerate an interstellar sail, would require vast energy, extraordinary optics, and precise coordination. The mission must operate longer and farther from support than anything humanity has built. Interstellar engineering is therefore filled with designs that are possible on paper, but separated from reality by entire industries that do not yet exist. The array would need to track the sail as it accelerated rapidly away. The spacecraft might weigh only a few grams, while the machine launching it becomes one of the largest scientific systems ever constructed. The starship becomes tiny because the civilization behind it becomes large. A future society with abundant solar energy and industry throughout the inner solar system might build such systems more easily. Interstellar travel might begin only after humanity has already become comfortable building on a planetary scale. It would depend on mines, factories, power networks, telescopes, and communication arrays spread across the solar system. This may be why the nearest star feels both almost reachable and impossibly far. The principles required to send a tiny probe are already understood. Light carries momentum. Electronics can be miniaturized. Lasers can be combined. Spacecraft can navigate without constant control. No new law of nature is needed. But every part must improve at the same time. The sail must be lighter. The laser must be more powerful. The aiming must be more precise. The electronics must survive stronger acceleration and longer radiation exposure. The transmitter must communicate across 4 light years using very little power. The receiving telescopes must detect the signal. A mission fails if only one of these pieces remains inadequate. There is also a question of patience. A 20-year crossing sounds short beside Voyager's 75,000 years, but it remains long compared with most scientific projects. The launching system could operate for minutes. Then the mission team would wait decades. Some of the engineers would retire before arrival. A few might not live to see the first data. The spacecraft would spend nearly its entire active story beyond reach, carrying equipment created with technology that grew older every year. During the wait, newer probes might be designed. A second generation could launch with better cameras, stronger communication, or a slightly higher speed. It might approach the first probe, or even pass it. Interstellar exploration could become a sequence of small machines moving through the same darkness at different velocities. The earliest probe would still matter because it began the path. But the first object launched toward Proxima might not be the first to arrive. The same uncertainty appears in larger propulsion concepts. A fusion probe launched after decades of development could travel more slowly than a later laser sail design. A civilization must decide when its technology is good enough to begin. Waiting could improve the mission, but waiting also delays every answer. No design will remove all risk. The first interstellar probe will probably be fragile, limited, and unable to stop. It may fail before leaving the solar system. It may survive the crossing and miss the planet. It may collect data that never reaches Earth. It may work perfectly and still return only a few faint images. Yet those images would represent a change no telescope can provide. They would come from the other side of the distance. The stars would no longer be observed only as remote light. Humanity would have placed an instrument beside one. That achievement would not make interstellar travel easy. It would show that the gap can be crossed by at least one kind of machine. Larger probes could follow. Some might carry magnetic sails for braking. Others might use fusion propulsion to enter the system more slowly. Networks of probes could relay signals, map hazards, and prepare for missions that remain near the star. The first arrival would become the beginning of an infrastructure, rather than one isolated event. But it would probably look very different from the arrival of a ship in a harbor. There would be no crew watching Proxima fill a window. No engine would gently settle the craft into orbit. No message would return immediately. A tiny probe would pass through darkness at extraordinary speed, record what it could, and send a narrow signal toward a planet 4 light-years behind it. The signal would travel home, while the spacecraft continued away from the star. Years later, instruments near Earth might begin receiving it. The people who had waited through decades of silence would not see the probe arrive. They would see evidence that it had arrived long ago. And once the machines capable of crossing the gap had become small enough to ride a beam of light, the final question would no longer be whether something from Earth could reach Proxima Centauri, but what the first arrival would actually mean when it lasted only moments and could be known at home only years after it was over. There would be no crew watching another sun rise through a window, no landing lights, and no voice announcing that humanity had entered a new world. A probe, smaller than a hand, could reach the Proxima Centauri system at a speed so great that the entire encounter passed more quickly than many missions spend orbiting a single planet. For decades, the spacecraft would have crossed darkness with almost nothing nearby large enough to photograph. Then Proxima would begin to brighten. Its planets, if they were positioned favorably, would slowly separate from the background, while gas, dust, radiation, and magnetic fields rose inside the instruments. Cameras might begin working before closest approach. Other instruments could measure the star's flares, the density of the surrounding plasma, and the conditions near any planets that crossed the route. If Proxima b appeared at the right angle, the probe might search for an atmosphere, temperature differences, cloud patterns, or signs that the planet had retained water. A fast flyby could reveal only one side of a planet and one brief moment in its climate. Proxima might flare during the encounter and overwhelm sensitive instruments. A planet could remain hidden behind the star or sit millions of kilometers from the planned path. Even an incomplete observation would contain something no telescope on Earth could provide. It would come from inside the system. The probe would see Proxima not as a faint red point, but as a nearby star surrounded by a natural environment measured directly. For the first time, a machine built near the Sun would have entered the space controlled by another star. At a significant fraction of light speed, the useful encounter might last only hours. The probe would cross the inner system and continue outward before Earth even received a signal announcing that the final approach had begun. Nothing near Proxima would slow it automatically. The velocity that made a journey of decades possible would carry the spacecraft away almost immediately. The first interstellar visitor might behave less like a ship arriving at a harbor and more like a camera passing through an open doorway at extraordinary speed. Several spacecraft launched along slightly different paths could observe the system from different directions. One might pass closer to Proxima b, another might study the star, and others could search for additional worlds or continue toward Alpha Centauri A and B. Some would fail during acceleration. Others might be damaged by dust, lose power, miss the target, or become unable to communicate. A few survivors could still transform what humanity knows. Their earliest purpose might be to test the route itself. They would reveal whether sails survived the laser beam, whether shielding survived interstellar dust, and whether navigation remained accurate after decades without repair. A torn sail would show which material was inadequate. A weak signal would reveal the need for larger receivers. Damaged electronics would guide future shielding. A navigational error would improve the accuracy of later missions. The first successful flyby might be followed by heavier probes using fusion propulsion, magnetic sails, or another method of slowing down. Those spacecraft could remain near Proxima, observe its planets for years, and build a clearer map of the system. Later, machines might use local asteroids and ice to construct communication stations, fuel stores, or protected habitats. A human mission, if it ever followed, could arrive in a system that robotic explorers had already studied for generations. It would prove that the distance could be crossed with purpose. Proof matters, because before the mission, interstellar flight would remain a collection of equations, laboratory tests, and proposed machines. Afterward, there would be a physical object that had survived acceleration, entered interstellar space, found another star, and sent information home. During the cruise, the probe could remain silent for long periods to conserve power. It would be too small and distant to track easily. Engineers might know where it should be, while being unable to see it directly. A missed signal could mean the spacecraft had failed. It could also mean its antenna was misaligned, its transmitter was weak, or it had entered a planned low-power state. Near the expected arrival, telescopes and receivers across Earth and space would turn toward Proxima. They would search for a signal weaker than the natural noise of the star and the background sky. That pulse would already be more than 4 years old when Earth received it. By then, the spacecraft would have crossed the system and traveled far beyond the point of closest approach. Its cameras would have finished their work, and its path would already lead into another part of the galaxy. The first close image of Proxima b might arrive slowly, carried by a weak signal over weeks or months. Computers on Earth could assemble fragments, correct errors, and gradually reveal the scene. It might be noisy, incomplete, or distorted by the speed of the encounter. Its importance would come from where it was taken. The probe itself might already be silent by the time the image was complete. Its power could weaken, its transmitter could fail, or its orientation could drift beyond correction. That return may sound small compared with the effort required, but many of humanity's deepest discoveries began with limited evidence. The earliest views of Mars were incomplete. The first detections of planets around other stars appeared as tiny changes in light or motion. A probe near Proxima could show whether our models of red dwarf systems were accurate. It could reveal whether Proxima b had an atmosphere, whether water remained possible, and how violent the radiation environment truly was. That result would still matter. It could protect future travelers from building their plans around the wrong destination and improve our understanding of billions of planets orbiting similar stars. A stable atmosphere would be just as important. Red dwarfs are the most common stars in the Milky Way. If a nearby planet survived in Active 1, the number of potentially habitable worlds in the galaxy could look very different. The probe might also search for chemical patterns connected with life, though any result from a fast flyby would need careful confirmation. A strange atmospheric signal could come from biology, geology, instrument error, or incomplete data. The most important discovery in history could lie beside a star 4 light-years away, observed during one brief encounter by a machine already leaving the system. A second mission would take decades. A larger probe able to stop might take even longer to build and launch. Proxima Centauri is too faint to see without a telescope, but it would no longer be only a point in a catalogue. Its planets could have measured temperatures, colors, atmospheres, and weather. The system would enter human memory in the way the Moon, Mars, Jupiter, and Saturn did after spacecraft visited them. It would remain distant, but the distance would no longer be completely untouched by human presence. The probe itself could continue for millions of years after its useful mission ended. Once its transmitter failed, it would become silent, like Voyager, carrying its damaged sail and miniature instruments through the galaxy. The spacecraft would never know whether its message arrived. It would execute its instructions, transmit toward the expected position of the Sun, and continue. This separation may define interstellar exploration. The physical traveler and the people who understand the journey may never share the same present moment. The mission becomes complete only when the signal reaches Earth, even though the encounter itself is already history. Some engineers who designed the probe may be gone. New telescopes may exist. Different institutions may operate the receivers. The data would arrive as both a scientific result and a message from an earlier period of human ambition. Interstellar travel requires cooperation across time as well as distance. One generation may design the sail. Another may operate the laser array. Later teams may listen for a signal from hardware they did not build. This chain of knowledge may be the closest thing to a bridge between stars. The bridge is not one enormous ship or a permanent road through darkness. It is a sequence of machines, experiments, and people, each extending the journey slightly farther than the last. Voyager showed that a spacecraft could leave the planetary system. Future sails may show that a machine can reach another star within decades. Later probes may learn how to stop. Only after those steps could a human voyage become more than a dangerous idea. The nearest star will not become easy to reach because one invention suddenly removes every limit. Progress will probably arrive through many smaller changes: stronger materials, more precise beams, lighter computers, better shielding, more efficient transmitters, and braking systems that slowly improve. Each achievement may look modest beside 4 light-years. Together, they could change the journey from impossible in practice to extremely difficult. Known physics does not forbid a probe from reaching Proxima Centauri. It demands energy, precision, patience, and acceptance that the first spacecraft may never stop or return. For humans, the requirements are far greater. A crewed ship must carry a living world, protect it, guide it, slow it, and preserve a society beyond rescue. The first arrival will almost certainly belong to a machine. It may carry only a few cameras and sensors. It may return less information than a modern telescope collects in one night. But if its signal arrives, it will confirm that something built near Earth crossed the space between stars and remained functional long enough to observe the other side. Proxima would not change. The distance would not shrink. Light would still require more than 4 years to travel between the two systems, while spacecraft moving at familiar speeds would still need tens of thousands. Before the mission, 4 light-years would describe a boundary approached only through observation. Afterward, it would describe a route that one machine had survived. The nearest star is almost impossible to reach because every problem becomes connected across the same enormous gap. Speed demands energy. Energy increases heat and mass. Mass makes acceleration and braking harder. Long journeys threaten machines, bodies, societies, and memory. Communication becomes years of silence. The destination may remain hostile even after every barrier is crossed. There is a sequence of ordinary physical limits. each becoming extreme because the journey is measured in light years. Every attempt teaches us more about propulsion, materials, automation, biology, communication, and long-term survival. Even missions that never carry people could create technologies useful throughout the solar system. For now, Proxima Centauri remains a faint red star hidden beyond ordinary sight. Its light reaches Earth without revealing whether its nearest planet has oceans, a surviving atmosphere, life, or only a silent surface exposed to radiation. Yet the first steps already exist. Probes have crossed the heliopause, light sails have flown. Lasers, cameras, and computers continue improving. Telescopes are learning more about worlds that cannot yet be visited. The first arrival may last only moments, beside a star that took decades to reach. It may be completed by a machine too small to see, followed by years of waiting for a signal carrying only a few images. But those images would mark the first time the darkness between the sun and another star had been crossed with purpose. Thank you for spending this quiet journey with me. If you enjoyed exploring the distance to our nearest star, subscribe for more calm space documentaries and leave a like to support the channel. Until our next journey, take a moment to look at the stars and remember that even the closest one is separated from us by an ocean of space larger than the night sky allows us to feel. For now, the nearest star remains where it has always been, close enough for its light to reach us and distant enough to remind us how much of the journey still lies ahead. Good night.